Apache wars only because people seem to view ActiveMQ and Kafka as, you know, competing messaging systems. And the purpose of this talk is to kind of lay out the differences between the two so that, you know, everybody in your audience there can understand or at least make educated decisions on whether or not one works for them over the other. Obviously, it's going to depend on use cases almost in every form, but a lot of times they have this misconception that Kafka is a messaging system. It works like a messaging system, but is not JMS compliant. So you can't just switch one for the other. Functionalities are fairly different under the covers also. So that's what we're going to walk through today, is making sure that you know, you get kind of a good understanding of what the differences are and how those are implemented. So without further ado, let's go ahead and take a look at what some of the differences that we'll look at. So when we take a look at like ActiveMQ versus Kafka, there's the concept of point-to-point messaging that we talk about in JMS, which is basically queue-based message transfers. So in the JMS spec, that's considered a queue. In the way ActiveMQ sees it, you are actually defining it as a queue. So that kind of becomes self-explanatory. But when you go to Kafka, there's really not a concept of queue versus topic, which is the next point, which is publish subscribe. Those are fairly separate concepts in the JMS world. In Kafka, they're really not. It's more along the lines of how do I assemble my consumers? And that's part of point number 3. We are going to take a look at how these consumers are set up for ActiveMQ versus Kafka, so that you guys get a good idea or understanding of the differences of how you structure the topology or the consumer topologies to make them function either as a queue or as a topic. The storage of the messages on the server is pretty drastically different between the two, and understanding how that happens behind the scenes will probably help you decide as to whether or not one works over the other. And then, of course, the high availability and what ActiveMQ provides for that versus Kafka. So those are basically the main high-level functions that we'll be discussing the differences in. So the first one we're going to walk through here is ActiveMQ. And I should have been playing this so you don't have to sit here and stare at my screen. Here we go. Makes it look a little prettier. Somebody should have yelled at me. So the first thing we're going to look at is ActiveMQ and how that functions from a queue standpoint. So the general operation there is you have a producer on ActiveMQ that produces to a queue in the ActiveMQ broker, and then you have a consumer that connects to that queue and is provided the messages. Now, in most of these types of scenarios, depending on configuration, the consumer is going to be pushed a message by the broker. The only time that doesn't happen is when you change the prefetch of the consumer. But the broker basically sends a certain number of messages to the consumer based on prefetch. And then the consumer chunks through them. And then as the consumer reads the message or pulls the message, it will acknowledge it back to the broker, and the broker will then delete the message off from the broker's data store, or out of in-memory, depending on your settings. So from a queue standpoint, it's really producer produces a single message, the consumer picks it up. As soon as the consumer acknowledges it, that message is now gone. So it's kind of a one-to-one or point-to-point messaging style, which is, you know, fits the JMS specification for that type of messaging. A topic-based is a little different in the idea that each subscriber is going to receive a copy of the message. So you have a single publisher which publishes the message to a topic, and then you have a subscriber that basically will register itself with the broker for that specific topic. And that's, it's basic topic messaging. But the difference there is that the way the consumer works in a topic type of structure is that the consumer is only going to receive messages while it's actually connected to that topic. So in what you see on the screen here, let me see if I can use my mouse. Yeah. What you see on the screen here is basically a timeline for the topic, right? So you have the first message number one that comes into the topic. The consumer is connected at the time that message is received. So it receives message number one. Now, if the consumer disconnects and message two comes in, you don't receive that message, and then it reconnects and you get 3 and 4. This is a basic topic functionality defined by the JMS specification. Now, other functionality that is, I guess, desirable is something that we're calling a durable subscriber, right? That's when a consumer, wrong direction, is able to disconnect but still receive messages that were on there during the time that it was disconnected. Durable subscribers are very risky to implement. They don't scale well, especially in ActiveMQ where you have a network of brokers. You can lock queues very easily, that you can fill up data stores. They just don't play nice in this environment. In most cases, when we're doing architecture type of design, we will steer away from durable subscribers at all costs unless there's only a single broker and we can maintain, the durable subscriber on a single broker that does not distribute its messages across any other systems. So that's just kind of I guess a word to the wise for durable subscribers. Definitely only use these sparingly when it comes to ActiveMQ. Oops, wrong direction again. Now, the way ActiveMQ gets around some of the, I guess, limitations of a topic, because in the spec, a topic doesn't allow you to have competing consumers. If you have more than one consumer connected to the topic, each consumer gets a copy of the message. That's how topics work. So ActiveMQ works with this in a way that it allows you to set up what we call either composite or virtual destinations. So in this case, we have a producer that produces to the code Denver order topic. Now, because it's a topic, we want to now utilize it as a queue. So the way we can do that is we can now forward messages out of this topic to the code Denver event pizza queue, and that is now defined as a queue. And that allows us to have, that is defined as a topic in this diagram. But you can set this up as either a topic or a queue, and then you can have the concept of either queue-based competing consumers, where you can now scale or distribute load across multiple consumers, even though you're getting the message from a topic. In a virtual destination, virtual destinations work similarly, but they're defined by the consumer. So in that case, you have a producer producing to something like a code Denver.order, but the consumer connects and says, I want to connect to code.denver.order with a specific prefix on that queue name, which then identifies it as a virtual topic or a virtual queue, depending on how you want to utilize it. It's a way to be able to change the behavior of a specific, either, I'm going to say a specific destination, so that you can then get around some of the limitations of either a topic or a queue. So you can make a queue function as a topic, or you can make a topic function as a queue by setting these up in the fashion that you see here. And composite just basically means that you're doing it through configuration in ActiveMQ, and virtual basically means you're allowing the consumer to define its interaction with that destination. So I was talking about having scalability or load balancing on a consumer. There's the concept also of like an exclusive consumer. So what you see in the diagram right here is you have 3 consumers, but you only want one to actually process the messages. And in most cases, when you do something like this, the idea there is that you want, or you have to preserve order from the queue. So in that case, you're literally only going to have a single consumer, because you can't guarantee order if you have multi-threaded consumers, you know, n number of consumers all processing off the queue, because one processor or one consumer may get more CPU utilization than the other, or they might be on slower or faster boxes. There may be network configuration or network issues, you know, whatever the state is. Obviously, you can't guarantee that in ActiveMQ. So the only way to guarantee that is, one, either having an exclusive consumer, or you can set up message group IDs. This allows you to now to basically scale the messages across multiple consumers, but locking a specific ID or set of messages to a specific consumer. So in the case of what you see right here, you've got a producer that identifies what group a specific message is a part of. So the producer is identifying, I am going to, you know, create you as part of group A or group B or group C, because I know that these have to be done in order. So it's going to produce those or push those to the orders queue in, it could be any order from a group ID, but that group ID has to, you know, the messages in that group have to be in order. And what that then does is it ties a specific group ID to a specific consumer. So in this case, you can see that the top consumer there is tied to the group ID of A. And what that then does is means that any message coming into that queue will be only processed by the top consumer. And groups B and C are tied to the consumer at the bottom. So only that consumer will be able to process B and C. You will see similar functionality when we get to Kafka, but it's done in a little bit of a different way. The next thing that I wanted to cover was high availability. ActiveMQ provides this from a standpoint of there's KahaDB, we have JDBC based. LevelDB is in red here because LevelDB is deprecated. That was also what was utilizing the replicated Zookeeper implementation for ActiveMQ. All of that is being deprecated at this point. So I would definitely suggest staying away from LevelDB and on ActiveMQ moving forward. But the way ActiveMQ sets itself up is, if you're using file-based or JDBC-based, it's similar type of functionality. You have one main data store, which is represented by that gray, you know, icon there. And the first ActiveMQ instance that spins up and gains lock access to either that file location or a table within the JDBC connection, wherever that's pointed to, whether it's MySQL or Oracle, whatever. Whichever one gains lock on it first is considered the master. Now, if that master goes down, loses that lock, then the slave becomes the master and takes it over. Now, you do have a single point of data. Now, obviously, people will replicate disks using SANs or you know, databases, nor like Oracle using, you know, multiple partitions across multiple systems that can be replicated. So there's ways, obviously, of maintaining that type of high availability, as well as data guarantees that you're not going to lose the data if something happens to the master or the data store itself. So ActiveMQ does it this way. So once the master goes down, the slave now becomes the master by obtaining lock. And the way it does that is the slave basically pings for lock on a consistent basis. So from the standpoint of just the high-level ActiveMQ processing, I'm not going to go into like the actual code base now. mostly what I want to do is just make sure that everybody understands how these processes, because I know some of you are probably familiar with JMS and how it functions and what it's supposed to do. Kafka does it a little differently, and it's good to know at least these differences that are out there. So in Kafka, the concept is similar. So as you can see from the diagram down below, we have a producer. This uses the Kafka Producer API, and it distributes a message to Kafka into a specific partition. So what we were thinking of as a queue in ActiveMQ, it has different partitions for a specific topic. So you could have n number of partitions on a topic. So when a producer produces a message, it's going to produce it to a specific partition. The consumer is defined by how the consumer group is set up. So in the case of this diagram, if we look at this from beginning to end, the producer is going to produce the message into Kafka to a specific partition. That partition is a part of a topic, but the message only lives on a single partition. Now the consumer is going to spin up a consumer group. That consumer group could have 1 to any number of consumers in it. But only one consumer in a consumer group is going to receive the message. So now you can kind of see or get the idea of how you may have an exclusive consumer in this process. And we'll go through this a little bit in more detail in a little bit. But the idea of queue now is that a specific consumer inside this consumer group will receive the message. So only one message is delivered to a single consumer. So here we have the concept of a topic. So each consumer group will receive a copy of that message, but inside the consumer group, it's going to receive just one message per multiple consumers. So I want to make sure that we understand kind of how this is set up. It's now the consumer that is defining how it interacts, or the consumer group that defines how it interacts with Kafka. Kafka really does not care how the consumer sees it, because from a messaging standpoint, Kafka is just taking a message and it's persisted almost like a log. And we'll go through that in just a minute. But the way it persists it is just a sequential file of messages. So we'll get into that in just a minute. But the consumer itself here basically is defining what or how it's going to communicate with that specific partition or multiple partitions. So in this case, you can see now we can interact with Kafka in either a queue-based system where a single consumer will receive every message off of that partition, or in a group of consumers that will, a specific consumer out of that group will receive the message. But each consumer group is now receiving a copy of the message, so the groups are at a level that it will be more of a topic-based. Topic-based, this is a queue-based. So if you want to treat a partition like a queue, you literally have one consumer group against it, and that's it. But the nice thing about it is that at no time does it prevent you from all of a sudden going, you know what, I want to treat this like a topic. So you're not predefining the functionality inside Kafka for a specific partition or topic. I'm always a little leery of saying topic because it predefines kind of what you're thinking when you talk about that message store, that destination, because it's not necessarily a topic. It's a destination that is defined by how the consumers are set up. So there's nothing stopping you from going from one consumer group to 3 consumer groups to 10 consumer groups. So you can dynamically change how a destination functions at any time, just based on how your consumers are utilizing it. So in this case, you can see that we actually have like consumer group 2, and then as we start to partition out or create new partitions for that topic, then we can actually utilize more consumers in a consumer group and scale to get better throughput. And you'll see a little bit more of that here in a minute. So the way a partition works, a producer is going to use the producer API to produce a message to a specific location. And the way to look at this is a partition is basically a log, right? So in this case, you're looking at it, you see 1, 2, 3, 4, 5, and the consumers actually define how they're going to read the message off of the partition. And the really cool thing about that is that you're not defined by what the partition feeds you, right? So what ends up happening is the consumer can say, I want to start at position 2 in the partition, or I want to start at the beginning. I want to start at position 1, or I just care about messages coming in from right now, from when I started. So I'm going to set my offset to the top level message in the partition. And these messages will live in the partition based on predetermined configurations. So when you set up Kafka, you get to define whether or not it's a time-based, we're going to keep these messages around for 2 days or 5 days or 10 days, whatever you decide. But the functionality is defined, or I guess the message consumption is defined by the consumer itself. The only thing that is actually persisted inside the Kafka server engine is the offset of the specific consumer. So the consumer can go in there and change. For example, the top one is offset of 4. Let's say he pulls message 4, starts working on it, something happens, something fails. The consumer can come back and re-pull message 4, or it could go back and say, you know what, I need 1 through 4 because there's a specific sequence of events that has to happen and 4 failed, so I have to do all of them again. So the consumer can define that, and the messages will be there. So that's part of the functionality that is easily defined within something like Kafka, whereas in ActiveMQ, once that consumer defines or has pulled that message and acknowledged that it's received that message is removed off of the data store and is no longer reconsumable at that point when you're looking at something like a top or a queue. So you can kind of see the divergence here from the standpoint of JMS specification implementation to something like this, which was originally designed for, I guess, high load streaming data and allowing the consumer to basically define how it's going to interact. For those of you that don't know, Kafka originated as, or was designed or built inside LinkedIn by a guy named Jay Krepp. And the concept here was high load, extremely fast processing for large amounts of data with persistence. That was the original intent of this. And the idea there was that they wanted the ability to be able to take stream data from, I guess, not logging, but event sourcing from web page events so that they could then process or identify, or I guess data mine that information at a later point. But in order to do that, they had to be obviously for LinkedIn, they had to be able to process huge amounts of data very quickly. That's where this came from. So they actually diverged from the JMS implementation to create something that really was not JMS compliant. They just needed to fix a specific problem for high load data systems and messaging, that type of thing. So that's where this stems from. And in order to make this highly scalable, full-on data persistence, that's where the partitioning of these basically kind of like data silos for a specific topic came into play, because all of these are now replicated across multiple machines, or can be replicated across multiple machines. And we'll take a look at that in just a minute. So from the standpoint of a specific topic, a topic can have a number of partitions on it, and they can be spread across multiple servers. So when a producer produces that message, it's going to know exactly which partition it wants to produce to. So that's how you get this kind of dedicated consumer processing, because inside a consumer group, there cannot be more than one consumer tied to one partition. So basically what that means is if you see like the top level partition 0, you've got messages being pushed to both consumer 1 of group 1 and consumer 1 of group 2. It will not display, it will not produce them like consumer 2 of group 1 or consumer 2 or consumer 3 of group 2. So only one consumer inside each consumer group will receive the message. But that's how you guarantee that kind of data flow, right? So that each consumer is guaranteed the order within a specific partition. So what we were doing in ActiveMQ from a standpoint of message groups, where the producer defined the message group, in this case, the producer will define what partition it goes to guarantee the order of the messages. And then these are then replicated across multiple systems. So if we're looking at how Kafka does that replication, right? So the producer produces to a single partition on a single server. That partition is replicated over to a second partition. And the nice thing is that that replication happens much like a consumer does who's listening on partition 1. So there might be a better, yeah, here. So what Kafka does is the followers in this case follow the leader. So what happens is when a message from a producer lands on partition 1, the leader then stores that message onto partition 1, and the followers then receive or pull that message from leader down to their local stores. And if you're familiar with Zookeeper, the way Zookeeper normally works, you have something like a quorum, which is kind of like a default set, or I guess a runnable set that basically defines that there is 3 out of 5 instances running, and that's your quorum. That doesn't necessarily work in this because in order to guarantee messaging, you have to make sure that every single one of the partitions in that replicated group have the exact information. Otherwise, you could promote one of the partitions to leader. If the leader goes down and the follower isn't exactly in sync with the leader, then you're promoting somebody who could be missing data. So what Kafka does is it's what they call an in-sync replica group. So everybody within this group has to acknowledge the fact that they received this message. Now, from a producer standpoint, you can have multiple ways of defining acknowledgements. So when the producer pushes the message to partition 1, you could tell it, I want to do it asynchronously, which means it will not wait for acknowledgement. You could do it with, I have at least one of the followers actually has acknowledged that it's received the message besides the leader, or you can set it up to all, which basically means all minus 1. So obviously, if you've still only got 2, you still have that possibility that there could be data loss if there's a complete catastrophic failure. But this is how Kafka sets this up. So it utilizes Zookeeper to replicate the data across multiple partitions, and these would be more than likely on separate servers. Partitions could be partitioned out on the same box, multiple boxes, but then it's just different layers of that leader, right? Because you could have 3 leaders with 3 different partitions on them, and then you'd have those same the same number of partitions on the followers also. So it's complete data replication across Kafka. So I already covered that. So from a standpoint of the acknowledgements, this goes into the all minus 1 versus the 0 and the 1. This way you're guaranteeing message delivery. Just like in ActiveMQ, the producer can sit there and say, I want to wait for acknowledgement out of the leader to verify that he received the message. Otherwise, if I don't get that acknowledgement, I'll reproduce the message just to ensure that we do get message guaranteed delivery. And then followers consume the message from the leader just like the producer consumes to it. And then there's a failover mechanism basically within Zookeeper so that once the leader goes down, it will be, it basically notifies the producer and the consumer from the standpoint that, it not really notifies them, but just changes who the leader is within the zookeeper, in this case, quorum or replicated in-sync replica, so that the producer and the consumer really don't see from a standpoint of, a failover or something like that. They're just partitioned or pushed to the next leader in the zookeeper quorum. So in ActiveMQ, we have the idea of being able to do embedded Camel or external Camel. What that provides us the ability to do is, if you produce a message to a specific queue and then you want to do some processing on it, you want to maybe do some transforms, maybe enhance the data, enrich the data, log the data, whatever. You could do that within Camel and then reproduce it back onto ActiveMQ to be fed to your external consumers or whatever. Kafka has the same kind of concept, what they call a stream processor. Now, this is kind of an embedded stream engine or stream API. Now, you run into the same types of issues that you have with embedded Camel within ActiveMQ. You've got this stream API that, while there are a few perks to being able to run it embedded, you also run into the problem that if you're doing major transformations or a lot of enrichment to the data, you're much better off externalizing that off from your Kafka servers. Unless it's something that's very simple and very in line with the data, simple transformations, that kind of thing. Same thing holds true with Camel and ActiveMQ. Most of the time when we're talking about those types of embedded processing, we always say externalize it, and that way anything that requires CPU processing does not affect your messaging engine in that case. One more thing that Kafka also provides is a connector API, which basically can read out of like an RDBMS, Cassandra, whatever, some sort of data store, right? It allows you to be able to connect via the connector API, and then what that does is then when you set up to listen to a specific like change events or things like that, you can feed those changes directly through Kafka to consumers. So in something like Oracle, where you have the change set events or things like that that get published as like triggers and that kind of thing, we can read directly off of the change sets and push those directly through to a consumer group or to another database. That's whether or not you're replicating data or something like that, or trying to be able to push or like migrate data, that kind of thing. So from the standpoint of some of the differences to keep in mind, obviously the way the file stores are set up is going to be different. You do have to be more cognizant of, especially with Kafka, how you're partitioning out your topics or destinations, and also how those are being replicated across multiple file stores, right? That's just making sure that your file systems are designed or configured in a way that provide high-speed access, and also can withstand the way that the data is stored, because it does things like batch writes and things like that. So in most cases, like Linux file systems are going to work great. Kafka on like a Windows base, I don't even think that's going to work, to be honest with you, but it is what it is. I don't think you should put anything on a Windows box, but that's just me. But also things like using the JDBC. So I mean, some people are married to the idea that they need the JDBC store for backing up the message or the messaging system. In those cases, basically you have to. Okay, I got to be careful about how I say that, because you could do it in Kafka, but it's not from a standpoint of a storage system, because the Kafka storage system is a log-based file system, right? But you could stream that data into JDBC if you needed to. ActiveMQ can utilize JDBC as your file store, so there's a difference there. Obviously, the performance of this is pretty drastically different. ActiveMQ, when you do everything in memory, you can probably get upwards of about 26 to 30,000 messages per second. That's, like I said, if you're pushing everything through memory, no, persistence, and everything is done in cache, and you've got high-speed consumers and high-speed producers. You can get upwards of about 30,000 messages per second. Kafka, with the file-based system, logs, and everything else, I've seen upwards of 150,000 per second, and they report getting upwards of 300,000 per second, but that's a way stronger machine than mine. But that gives you an idea of just the sheer throughput that something like Kafka can give. But again, once you go to something like a Kafka system, it's not something where you can just switch out based on JMS implementations. You don't have multiple different like connection mechanisms, or switching out how the underlying store saves its data, things like that. You're kind of tied to the specific structure of Kafka. ActiveMQ, as far as the embedding the integration engine like Camel. Kafka also has Camel endpoints on it, so you can either Kafka or AMQ. Obviously, the difference with Kafka is that you have the embedded streaming engine or API, which is optimized specifically for Kafka. Being able to scale your components or your consumers. When you get to a certain point, your scaling of your consumers is tied to the number of partitions you have. So if you have a specific consumer, in a consumer group, so you have a consumer group of 5, let's say, and you have 5 partitions, that's the highest you can get on your consumer count within a specific consumer group. Because after that, each consumer can only be tied to one partition. If you add another consumer to that partition, and it'd probably be good if I go back to the screen just so you guys can see it. Here we go. So from this standpoint, once you tie a consumer to a specific partition, you can only have as many consumers as you have partitions. So in the case of what you see here, consumer group 2, if we wanted to add consumer 4 to the consumer group 2, it would not do anything at that point, because it cannot produce more messages to another consumer in the consumer group without it being tied to a specific partition. Now, you can have multiple partitions to a single consumer, but you cannot have it the other way around. So that's something to keep in mind. So if you do decide that you need to up the number of consumers in a specific consumer group, then you also have to up the partitions, which now changes the dynamic of that topic. So your producer also has to know that there's a new partition out there if it's doing things like specifically identifying which partition it's going to produce to. Now, the one thing that the producer does have, or the producer API, is that it has the capability to say, I'm going to round robin my messages. So you don't have to sit there and worry about, okay, well, I've got 5 partitions. I need to send them, each message to each partition. The API has the capability to say, okay, you want round robin? I'll just distribute the load across all of the partitions, sending one message to each partition and then circling back, and so on and so forth. That provides you the ability then to just load balance across the system. Sorry, moving back to the differences here. And one of the other pieces that a lot of people always ask about is going to be monitoring. How do I monitor these systems? AMQ has a web console that one is provided, but they also have, there's separate monitoring consoles that are available. Kafka does not have one that's embedded or provided as part of it, but it does have an external project that you can use or you can download to view the Kafka infrastructure. So you can actually see what consumers or consumer groups are attached to your specific leader in this Kafka topology. You can also utilize JConsole or virtual JVM to be able to connect to MBeans to be able to see some of the statistics also. So much of the same monitoring is available either way. And because they use MBeans, you have the ability to attach to these through most of your monitoring systems. So from a standpoint of being able to monitor these systems, both of them kind of have good and bad aspects to the web console. By no means are they fully featured, but they provide you at least eyes on target to be able to see what these look like. And then, of course, the last thing I want to just kind of lay out there is that Kafka is not a JMS compliant engine. It's not meant to be. It wasn't designed to be that way. Again, it was designed by LinkedIn to solve a specific use case, which they, and believe it or not, in their use case, they actually tested ActiveMQ and tried ActiveMQ in the configuration of what they needed, and they could not get it to function in the manner that they needed. So that's where Kafka came about. But is it fully? Does it have all the capabilities of ActiveMQ? No, it does not. Especially from a JMS compliance standpoint, people who want to switch over to from one messaging engine to another can do it in a fairly simple manner when working within a JMS compliant engine. Once you go to something like Kafka, it's a completely different implementation. So that's really where the changes come in. And then understanding how those messages are distributed across the partitions, how you can manage those either from a consumer or a producer standpoint. Because when you work with something like ActiveMQ, it's kind of hands-off. Once you get a producer producing onto a queue, the consumer attaches to the queue and pulls it off. You get one at a time, everything's hunky-dory. And if you add more consumers to it, the queue still functions as a queue. You don't change that functionality or the way that functions just by adding or removing consumers. With Kafka, it changes how it receives messages by adding or removing consumers or consumer groups. And that's the biggest understanding that we're trying to get out there to make sure people understand the differences of how those consumers get the messages and how those messages are stored inside the engine itself. So who is the winner? And I know from the standpoint of the way I present it, it would sound like Kafka is a clear winner here, but it really depends on your use case and the way, and from I guess market acceptance. Right now, ActiveMQ is still a clear winner here from just market saturation and how many companies have implemented it and used it. So in that sense, from an Apache war standpoint, ActiveMQ is probably the empire and Kafka is going to be the rebel alliance, right? So they're slowly gaining acceptance in the community. There's a pretty steady incline of interest when it comes to Kafka, but because they broke the mold of how JMS is used or is thought of, it's taking a little bit longer for it to gain acceptance in the market. But there is a pretty steady stream of it, and we're seeing more and more of it from, as an Apache consultant, of interest inside of this, mostly because of just the sheer throughput of the messages. When you're talking something like 150,000 messages per second based on the best case scenario for ActiveMQ is 30,000, but once you implement persistence and all that, I mean, depending on message size and the way the infrastructure and the topology is set up with a network of brokers, you could basically be looking at maybe 100 messages per second, depending on some of those topologies. So there's a fairly significant difference there, and then I think that's why Kafka is really starting to gain some of the popularity that it is. So at this point, I'll open it up to any questions you guys have, or You know, I don't speak Spanish, I'm sorry, so I'll need somebody to translate.
Hello, this is Roberto Salazar here. I just have one question. It's totally different against these technologies. I want to know if you know something about SQS, what is better against Kafka or ActiveMQ?
I have not seen SQS from a Kafka standpoint, so I honestly can't speak to that. So yeah, I mean, knowing which one would be better there. I mean, I've never actually seen Kafka being utilized with you know, SQS, unfortunately. So I really don't have an answer for you.
Thanks, no problem. Thank you.
Thank you.
Any other questions?
Any more questions?
Hi.
Heath, I really appreciate your help. And
I have a question.
okay, Jason, go ahead.
Thanks. You mentioned that Kafka is not a JMS complaint engine, but at this moment, do you think it is it's the best alternative in case you have a microservice architecture? What do you think about that? I understand not every system is a microservices capable to implement it. It's not possible to implement any system as a microservices one. But I just want to know if you think Kafka is a good choice for that case, for a microservice architecture.
Yeah, that's actually a very good question. Because I mean, I guess I'm going to think of microservices from the standpoint of you know, a lot of partitioning of communication between those microservices. So if you're looking for an engine that is still optimized for those, I guess, you know, microservice type of, you know, communication, in most cases right now, most of what we have worked with and done has been in the ActiveMQ arena. So from a standpoint of like system acceptability, ActiveMQ has been out there more and developed against more for the microservices. Kafka is an interesting concept because it's not, you know, most of the places that I've been in that we've worked with Kafka have been these high transaction type of load systems, not necessarily for these small, quick interaction type of services, but these large, let's get a ton of data through to, you know, a back-end service, data migrations type of things. Up to this point, that's been the I guess the more popular implementation for Kafka. With that being said, if somebody's willing to you know, jump into the bleeding edge of what Kafka can do, I think I think it would be really, really powerful and capable. But again, it's hard to sell that to a corporation that's already invested in something like ActiveMQ or some other messaging system, right? To bank their entire microservices deployment engines on a and I say fairly new, it's, you know, in 5 years old maybe that it's been around since LinkedIn started, or, you know, came up with the concept of this to begin with. but because it's not JMS compliant, it's one of those that's harder to sell, right? So from my standpoint, I would love to get into a project that allowed me or gave me the flexibility to actually prove that out. But right now I haven't had the ability to take Kafka into a microservices type of environment. You know, I know that was a long answer to a very simple question, but I guess I wanted to make sure you understood, you know, kind of why. The answer is I don't really know.
Okay.
And one last question, in this topic, you are part of the, are you part of the empire of the resistance?
I'm kind of like Darth Vader getting pulled over to the Rebel Alliance, right? Because I've worked in ActiveMQ for a very long time. So it took me a while to come around to what Kafka is doing. But right now at this point, I'm very intrigued about what we've done with Kafka up to this point. And I look forward to seeing more of it and just a higher acceptance in the community as far as what it can do. Because I like the concepts. I like what they did. But again, it breaks the JMS compliance, right? So it's a hard sell to people who, you know, are very ingrained in you know, specifications. So I know that also was kind of a non-committal answer, but I'm looking forward to working more in Kafka. Let's put it that way. I love ActiveMQ. I think it's very capable. But there are systems, there's been quite a few systems in the past, probably 3 years that I've worked on that I think Kafka actually would have been a better implementation. I'll give you an example. Do you guys, are you guys aware of Ticketmaster? By chance, it's basically a ticketing system that we use in a lot of the English-speaking countries anyway, from like Australia or the US or, you know, places in Europe. They control all of the tickets that get sold at venues for like sporting events or concerts or things like that. They have a very, very large throughput requirement when it comes to selling things for, I don't know if you guys ever heard of like Kid Rock or, you know, popular artists that sell their tickets all at the same time. So like Kid Rock and Taylor Swift, which are, you know, a couple of our very popular artists, go on sale at the same time, and they sell probably upwards of 75,000 tickets in a matter of minutes. But those ticket sales equate to 7 or 8 million transactions within a couple of minutes that all have to be processed. And when you have multiple of these sales going on, you can see that it takes a lot of load to be able to process those. We've had to architect around those systems when we utilize something like ActiveMQ, because ActiveMQ obviously cannot process that amount of load. Something like Kafka is very interesting in that type of architecture because it doesn't matter how large your queues or your destinations grow to because of the way the logging system and the indexing is set up. So whether you have, you know, 500 kilobytes in there or 50 gigabytes in a queue, it doesn't affect performance hardly at all. I hate to say it doesn't affect it at all, but it's very slight when you start growing these queues to large proportions. Whereas ActiveMQ, the more data you put in there, the more you'll see degradation in performance. So I'm interested to see where Kafka goes, and I'm definitely interested in becoming more involved in that community, and then also looking at the different solutions that are out there for it, or that, you know, that have utilized it.
Great, thank you.
So I think that we are done.
Okay.
I really appreciate your help and your collaboration, Heath. I will see you soon. You later. Maybe I'm going to speak now a little bit in Spanish, but
Definitely. Thank you, and we'll chat again soon, I'm sure.
yeah. Thank you. See you. See you later.
Definitely.